So the final speaker of the first session is Joana Farinhas, and she will talk about efficient PTB7-based ternary organic photovoltaic cells.
Good afternoon. First of all, I would like to thank the organization for this opportunity to talk about ternary organic photovoltaic cells, a work developed under my PhD, so it's recently. As you know, there is a wide range of strategies to optimize the organic solar cells, despite of using more efficient materials. We can incorporate additives to the solutions. We can submit the organic active layers to solvent or thermal annealing. We can prepare inverted structures, or even, or even prepare more complex architectures, the so-called tandem solar cells. These devices has the advantage of combine different materials with different energy gaps to enlarge the absorption range. However, the ternary solar cells have been explored as an attractive approach to increase also the absorption range, combining also different materials with different energy gaps, taking the advantages of tandem cells, but in a single layer. There is several categories with respect to the surge components, to the electronic nature of the surge components on the thermal blends. The more common are 2 electron donors and 1 acceptors, or 1 electron donors and 2 acceptors. Concerning to the morphology, the surge component can be integrated within the dominant binary blends, with different rearrangements. The surge components can be fully embedded, on the donor phase, or on the acceptor phase, or located at the interface between the donor and the acceptor, or forming its own domains. And this morphology could be the best morphology for the ternary systems, because each pair of donor and acceptor may work independently of each other. So these devices present more complex systems than the conventional binary devices due to the higher diversity of the materials and the properties and the more complex morphology. However, they have the advantage of combining different materials to enlarge the absorption range, combining with the simple process to prepare single layers. And the presence of multi-components may improve the charge transport and reduce the charge recombination. Here, I will show you a ternary system composed by 2 polymer donors, the PTB7 and F82, and 1 acceptor, the PC60BM. The PTB7, as you know, is a high-performing polymer with efficiency higher than 9% combined with the PC60BM. When the PTB7 is blended with PC60, BM, the efficiency is around 4 to 6%. And the F82 present much lower performance, but is a polymer widely applied in electronic devices due to the good charge transport and higher crystallinity than the other polymer donors. From the optical spectrum, from the absorption, we see that the F82 has a maximum absorption located at 450 nanometers, blue shift with respect to the main absorption band of PTB7. So combining these 2 polymers donors, we almost cover all the absorption spectra. In addition, the photoluminescence of F82 partially overlaps with the absorption of PTB7, which means that the F82 may act as a photosensitizer for the PTB7. So the photons emitted by F82 can be absorbed by the PTB7, and more excitons are created at the PTB7 face and can be separated at the interface between the PTB7 and the acceptor, the PCBM. The relative energy levels of the two polymers make them the donors with respect to the PCBM. And if we analyze only the energy levels of both polymers, we see that the F82 can transfer its energy to the PTB7 and support our assumption that the F82 can behave like a photosensitizer for the PTB7. The protocol that we used to prepare the ternary or binary solar cells was the same. We used the same concentration of solution, we used the same solvent, we used the same spinner velocity. We only change the ratio between the two polymers on the ternary, but we keep the constant if we relate with our reference cells. So the ratio between the donor and the acceptor was 1 to 2, and this was kept the constant when we prepare the ternary cells to directly comparison between the ternary and the binary cells. Here I present you the performance of the devices. As you see, we have binary systems composed by F82 and PCBM, and we achieve an efficiency of 2.67%. Here, the other binary cells composed by PTB7 and PCBM, and the efficiency is much lower, 3.79. And for ternary cells, we studied 4 compositions. And for these two, we increased the performance around 30%, comparing to the most efficient binary cells, PTB7, PCBM. And as you see, the fill factor is the parameter that is most affected. And if you note, the VOC is very similar and close to the PTB7 binary cells. So we may conclude that because this VOC is similar of the VOC of these binary cells, that the F82 actually may act as a photosensitizer, and the charge separation mainly occurs at the interface between the PTB7 and the PCBM. Here, I present the external quantum efficiency for the most efficient ternary cells and the binary, both binary control systems. And as you see, we show an improvement of the intensity on the F82 region, complementary to the PTB7. So we have an enlargement of the absorption spectra because we increase this region. But again, due to the VOC being close to the PTB7, these the F82 polymers may act as a photosensitizer, and the charge separation occurs at the interface between the PTB7 and the PCBM. We also investigate the topography of all ternary systems. For the case that we have the same amount of both polymers, the F82 and PTB7, we obtain a relatively homogeneous surface. However, When we decrease the amount of F82 on the total of mass of polymers, we obtain a segregated surface with these circular domains. We also analyze the topographic image of films composed only by the two polymers without PCBM, and we see that for this case, we obtain again an homogeneous surface, but for these three cases, we obtain again a segregated morphology, which could be related with the segregated morphology on the ternary blend films. So we conclude that for a certain polymer ratio, we obtain a segregated morphology, a well-not miscible phase of polymers that we not obtain for this case. We also analyze by scanning transmission X-ray microscopy the composition of this phase, this segregated morphology. And this part of work was made by a successful collaboration with Professor Ellen Moons. So I hope to not say anything wrong. We first of all, we measure the films of pure materials, and then it was possible to generate this composition, the chemical composition, compositional maps. And we conclude that the circular domains, and here we have the two more efficient ternary devices, the layers used in the more efficient ternary devices, and we conclude that these circular domains are enriched in F82 polymers, and the phase that surrounds the circular domains is mainly enriched in PTB7 polymer. The PCBM that we not show here, due to the lower contrast, we believe that the PCBM is eventually distributed within the two phases, mixed with PTB7 and with the F82. So, we conclude that in this type of morphology, both polymers may adopt the most favorable molecular ordering, and the centers of recombinations may be reduced when we compare with the more homogeneous surface of these kind of ternary blends. And of course, in the case that the polymers are immiscible, we can prepare efficient devices, not only when we have a separated phase without any aggregates, any domains. Here we have isolated domains of one polymer, and even so we obtain an improvement of the efficiency with immersible polymers. The second part of the work was made only replace the F82 by a cross-linkable derivative. And this cross-linkable derivative was used to study the stability of the cells when we have a more rigid layer after the cross-linking reaction. This polymer is not commercial, was synthesized in our group by Dr. Ana Charas. This polymer is different from the F82 because this polymer has an oxytane group at the end of the alkyl chains that can react via cationic ring opening polymerization at the presence of H+. This H+ is released by this photoacid under UV illuminations. So, from this ternary blend, we use the same PTB7, the same PCBM. We replace the F82 by this F82OX1. The concentration was the same, everything was the same, but we use this polymer and a minimum amount of photoacids. We submitted these active layers to a cross-linking protocol. We illuminate 1 minute at UV light, and simultaneously we heat at 100 degrees, and then more 5 minutes under dark conditions at the same temperature, and we obtain layers cross-linked. And our goal was to compare the stability of the devices with the cross-linked layers and with non-cross-linked layers. We try two different compositions of polymers, and you can ask me why do not use the most efficient ratios that you studied before, because here we study the less efficient ternary system. But the yield of the cross-linking was directly related with the amount of F82OX1 that we have on the blend, because it's the F82OX1 that will cross-link and not the other materials. So we studied these two, the non-cross-linked and the cross-linked cells, and as you see, the two ternary cases are both less efficient than the most efficient binary, and when we cross-linked, we decrease even more the efficiencies. And this can be related with two factors. First of all, the whole mobility decreased a lot when we cross-linked the polymer, and on the other hand, the PTB7 is affected by this cross-linking reaction. We see a reduction of the intensity of the peak of the PTB7 when we cross-linked the layers. So this may be related with this lower efficiency when we cross-linked the active layers. However, if we analyze the stability, we see that in the case that we have a cross-linked layers, we have a more stability with respect to the active layers non-cross-linkable. So the devices where when the active layers will not submit it to a cross-linking protocols, degrade more than the devices where the active layers are cross-linked. However, as I told you, we have a detrimental effect on the PTB7 contribution, so the alternative is promote this cross-linking reaction through temperature. We study the minimum temperature and time to cross-link the pure polymer donor, and we apply on the ternary blends. Here I show you two conditions of temperature and time. For this case, we decrease a lot of the efficiency, but I'm sure that it's because this higher temperature that can be detrimental to PTB7. But here, with the thermal cross-linking, we slightly increase the efficiency. And with this thermal cross-linking, we do not affect the PTB7 contribution. So as you see here, it's the EQE comparing the non-cross-linked cells with cross-linked, and in this case, we maintain the intensity of the PTB7 region. So without photoacids, we don't degrade the PTB7. We also measure the stability, and the blue is the cells cross-linked, the black is the cells non-cross-linked, and we have at the end of more or less 1,000 and almost 1,500. We reduce less the efficiency when we use a cross-linked layers in comparison with the non-cross-linked layers. So we can conclude that these cross-linkable materials, or a family of these cross-linkable materials, may be a good strategy, not on these systems, because PTB7 could be affected by the temperature, or by the photoacid, but in other systems, these cross-linkable materials may be a good strategy to improve the stability of the devices, because a cross-linked layers is more rigid, avoid some rearrangements of the polymer chains, the diffusion of PCBM, and gain on the stability. This is the conclusion that I told you during the presentations, and I would like to thank my group, Professor Ellen Moons, and the Cost Action for allowing me to visit another group during 2 weeks to develop some studies. And thank you to the audience.
Okay, thank you very much. We have time for one quick question, if there is one.
Me again. Thanks a lot. A very quick question to the morphology you have been observing. That looked quite interesting for the ternary blend. So were these all separated from each other? I mean, it looked like multi-scale phase separation in some sense. I mean, when you go from the binary systems, I'm talking about the AFM
in binary
images.
systems, we don't have any phase separation. The PTB7, PCBM.
Well, I talk about those AFM images, and I talk about the ternary systems.
The ternary, okay.
And I wonder whether you analyzed it in more detail, how the distribution of phases there is, and if that could be some kind of multiple scale phase separation, like first the two stay together and one separates, and then those two other phases separate from each other. Just a question. No.
No.
Thanks.
Okay, on that note, let's thank the speaker again.